We're going to take a look at Newton's versions of Kepler's laws problems, worksheet number 2. I'm going to work them out for you in this video, and I'm just going to do problems 1 through 4 in this video, and then the others I'll do in a second video. So if you're interested in the other ones, check out the second video. Before we start working them, let's take a quick look at the equations we have. We have, of course, the force of gravity equation, Newton's universal law of gravitation. We have this one here, which has period in it, period being a special unit of time that it takes to make a complete orbit. And of course, in that equation, we have the large m. The large m means the planet. We also have here the orbital velocity. The orbital velocity is how fast the satellite, planet, or whatever is orbiting whatever it's orbiting. And again, we have the large m in here. The large m is the planet's mass. And then over here we have Kepler's law. Kepler's law is just a relationship between two planets or two satellites. You need to compare them to something that is orbiting the same system. So over here in this corner we have little g. Little g can be called the acceleration due to gravity or the gravitational field, or sometimes gravitational field strength, or sometimes the strength of the gravitational field. Those are different than F sub g. F sub g is the weight or the force of gravity. And of course we have that other old equation for force of gravity, F sub g equals m little g. And that leaves one last equation. It's this guy right here. It looks just like the orbital velocity, only it has a 2 in it, because this one you need to escape the planet. This is the escape velocity. Which one of these equations we use depends on the information given to us in the problem. So this is where identifying your knowns, unknowns is powerful, so you can then figure out which equation to use. Okay, enough of the review. Let's look at the first problem. What is the velocity of a satellite that is 300 kilometers above the surface of the Earth? We're going to write down our knowns and unknowns. Okay, I've written down what I know and what I'm hunting for, and it doesn't really help me a whole lot, except that I'm hunting for velocity. So if I'm hunting for velocity, if I go back up and look at my equations, that's narrowed down my equations to 2. I've either got this guy right here, which is the orbital velocity, or this one right here, which is the escape velocity. Since it doesn't say anything about escaping, I figure I'm going to have to use the orbital velocity. So actually, that does help a bit. Okay, we've written down the formula, but we don't have everything. We don't know what big G is. Oh, yeah, we do. That's a constant, so that's easy to put in there. We don't know what the capital M means. It's not given in the problem. Oh, but wait a minute. We've listed what the mass of the Earth is, so we've got that. Okay, so we know what M is. We just have to write it down. And then what's R? Is R the radius? Is it 300 kilometers? Well, no. Remember, R is the distance from the center of one object to the center of the other object. So let's draw a quick picture to visualize this. Okay, the information I have in the problem is that the satellite is 300 kilometers above the surface of the Earth. But this R over here is from center to center, so I need to include this distance here. But this distance here is the R, or radius, of the Earth, another piece of information that's been given elsewhere. So let me write down the information that we had to get from somewhere else, not from the problem. These 3 pieces of information are given to us in another location, but they're going to help us solve this. This radius of the Earth we're going to have to add to 300 kilometers. But note, this is in kilometers, and this over here is in meters. So I have to change 300 kilometers to meters. So I'm going to go ahead and do that. So 300 kilometers is equal to 0.3 times 10 to the 6 meters. So I can add those together, and I get 6.68 times 10 to the 6 meters. So the distance our satellite is from the center of the Earth is a total of 6.68 times 10 to the 6 meters, which is that r, the distance from center to center. Now I'm going to take all this information and plug it into my equation. Once I get it plugged into my equation, I'm going to grab my calculator and solve it. This particular equation doesn't have too many order of operation problems, so you can probably do it all as one step. So you want to multiply 6.67 times 10 to the minus 11th times 5.98 times 10 to the 24th. That gives me on the top about 3.99 times 10 to the 14th. Now I'm going to divide that by 6.68 times 10 to the 6th. And that gives me 597,104,79. I'm going to take the square root of that, and that gives me the answer. And voila, we have the answer. 7,727.26 meters per second. Let us now move to the second problem. How far above the surface of the Earth is a satellite if it has an orbital period of 5 hours? So this 5 hours is information, and 5 hours is the orbital period. But remember, orbital period is that special time that's made a capital T. So we know here that capital T is equal to 5 hours. Okay, and we want to know how far above the surface it is. So we want to know the distance above Earth. A quick sketch here would be nice. So again, I'm going to just draw the Earth, I'm going to draw the satellite, and what we're really hunting for is this distance here. Okay, so this is our unknown. But in any of the equations, what we're given in those equations is this big distance here from center to center. That's what r equals. I'm going to go ahead and solve for r to begin with, and then we'll find out what d is after as a second part to this problem. So we've got t. That's really helpful. We're trying to find r to begin with. So we want an equation that has t and r in it. Let's go up to our equation list. Okay, we have two equations with t in it. We've got this guy, and we've got this guy here. Now, Kepler's law, the one I'm coloring in right now, is only good if we have something to compare it against. And while we could compare the satellite to the moon, we're not going to. I'm going to use instead the other one with period in it. So by virtue of elimination, that's the only other one with period in it, so we're going to have to use that equation. We're just going to figure out how in a minute. So let's rewrite it down by our problem. Okay, we're going to be solving for r, and r is in the equation. So that's good. We've got that covered. We've given t, so t is right here, so that's good. We've got that covered. 2 is just a number, so we know that. Pi is just a number, so we know that. Big G is a constant, so we know that. This m, what is big M? Well, if we're talking about going around the surface of the Earth, remember the capital M is the mass of the planet you're orbiting. So this big M is the mass of the Earth. And we have that information, just not stuck in the problem. So we have to look somewhere else to get it. I'm going to list the things that we know from somewhere else. So we've got those guys listed, and we could plug and chug, but we've got to remember that if we're using big G and capital M, we're going to have time in seconds. And right now it's in hours. So I'm going to have to convert that. So I'm going to go ahead and do that quickly. So I've quickly converted my period, my orbital period, from hours into seconds using some nice dimensional analysis. So now I've got the t, I've got the g, I've got the m. I'm going to start plugging it all into my equation so I can solve it. Okay, I've got it plugged into my equation. Now I have to do my algebra. There's a temptation to square both sides first, but if you do that, most people forget to square the 2 pi. So first I'm going to get 2 pi on the other side. So I'm going to have 1800 divided by 2 pi. And the calculators are all making the mistake. If you don't put the parentheses in there, you're not dividing by 2 pi. You're taking 1800, dividing it by 2, and then multiplying by pi. So if you do it as 2 separate steps, be sure and use a parenthesis in your calculator. So that step gives us 2864.79, and that's equal to that radical and all the stuff underneath the radical. So now I'm going to square both sides to get rid of the radical sign. So I'm going to take this number and square it, and I'm going to take this big thing and square it. That gives me that number, and now I'm going to multiply both sides by the denominator to get that out of the denominator. So I'm going to take this side and multiply it by big G, and I'm also going to multiply by the Earth's mass. And so these will be multiplied, and these will be multiplied, and these guys are going to cancel out. Let me go ahead and do that. My in-between step is I get 3.27 times 10 to the 21st equals r cubed. I'm going to go ahead and take the cubed root of both sides. Okay, I get 1.485 times 10 to the 7th meters is equal to r. But that's not the final answer. Going back up to our original drawing, what we wanted is not the radius, which is what we just found. It's at 1.48. But we want to know the distance above this. So to get that distance, we're going to have to subtract the radius of the Earth from the big number. So I'm going to go back to my big number. And when I subtract the two, I get the distance above the Earth is equal to 8.47 times 10 to the 6 meters. And that is the final answer. Moving on to number 4. An asteroid is in the Earth's orbit. The people of Earth wish to colonize it, but are concerned about the gravity on its surface. It has a mass of 2.4 times 10 to the 24th kilograms and has a radius of 2,500 kilometers. Find the magnitude of gravity, the gravitational field, so they can decide if they should colonize the asteroid or not. Okay, well first I'm going to write down what we know. I've got a mass here, so I know I'm going to have a mass. And I've got a radius here, and I'm trying to find the magnitude of gravity. And then the author said gravitational field. Okay, so I've written down what we know, the mass of the asteroid, the radius of the asteroid, and gravitational field is little g. So going back up and looking at my equations, there is only one equation with a little g in it. It's this guy right here. So that looks like the equation we're going to be using. Okay, it's got a mass and it's got a d. What is this d? Well, remember d and r basically are the same things. So it's an r. Let's go down and rewrite that equation and solve the problem. Okay, we got to be a little careful here. This has a big M. Big M is the planet you're orbiting around or the planet you're standing on. And we're standing on the asteroid. So big M is indeed the asteroid's mass. D, we said, is the same as the radius. And it's the radius of the planet, center to center. You're standing on the surface of the planet. Therefore, the radius of the planet, or the asteroid, is equal to the distance you are from the center. So we've got that. Of course, we know what big G is. So I think we can go ahead and plug and chug and get an answer. Okay, we've got the numbers plugged in. There's only a couple of things you need to be careful about with this equation. One, a lot of people forget to square. So you've got to remember it's a square down there. And two, the original radius was given to us in kilometers. So you have to remember to change it to meters. I like to do that right away up here because then I don't forget to do it. So we've got to make sure this is in meters, and we've got to make sure to remember to square this. Otherwise, there's nothing really very tricky about this equation. Okay, when you plug in the calculator, you get little g is equal to 25.61. And because we're talking about gravitational field strength, which is also the same as the acceleration due to gravity, the units ends up being meters per second squared. And you should be used to that because you've had 9.8 meters per second squared. We could derive these units, but they get pretty interesting because this guy, big G, is just a large number of bizarre units that all ends up canceling and changing, and you magically get meters per second squared. And I'm magically done with problems 1 through 4, having skipped 2. And I'm going to end this video, and in the next video I'll address some more problems. Thank you very much for your time.